variance that we get estimated based on that 95% confidence upper limits and detection significances. And what turns out is that, for instance, in the case of Effelsberg, there are good chunks of data where the noise that we see really corresponds to what you expect from the radiometer equation. That's nice, but there are also clearly regions where there's just much larger noise. In the case of GBT, we were kind of a bit foolish because we didn't ask for high, so the energy resolution that we have there, the frequency resolution is quite bad, which means that we are never in the really statistics limited regime where things agree with radiometer equation, but always apparently dominated by some systematics. So there the limits are somewhat weaker than we would have expected. Ask for different receivers in the future. Good, so these are the upper limits on the flux density that one obtains, so that's all preliminary results, so this is what we have right now, but there's not too much wiggle room left. This is for Effelsberg, the black lines, and GBT corresponds to the blue lines and various other colored lines. So the flux upper limits, which correspond to upper limits on these individual frequency channels that we have, are typically at the level of 100 milliansky or something like that. Which is not too bad. It was a bit worse than we expected, but if you now compare this with the expected signal, flux, one can translate this into limits on the axion photon coupling. So this is now again the plot that I showed very much earlier, just a zoom in to the interesting parameter range. So you see we cover very narrow range of axion masses here just from 10 to 11, and here from 5 to 7, but it's like the first time these searches have been done. But what's interesting is we actually get with these limits below what we had before from the sun, so below the cast limits. And actually quite significantly below, so this is like 1 to 2 orders of magnitude below. And if you think about future extended versions of cast, they also will just get down kind of here. So it's very competitive already now, even after using only a small amount of data. This here is Effelsberg data from observations of the galactic center. This here is also Effelsberg data from observations of the galactic center, and the other lines here correspond to various other targets. Good, so that's actually a very nice result. You see that this here happens to be already excluded by direct lab experiments, but here actually this is not excluded by anything up to now. A caveat of this, a strong caveat, is that since these are galactic center observations, even if you can be if you pretended to be super sure about our signal calculations, there is still the uncertainty that comes from the dark matter profile itself. So if it's a Caspi profile, FW profile, as we assume here, the signal is expected to be quite large. If you assume core profile, the limits jump up. Yeah.
You must also be sensitive to uncertainties in the population model of the stars and the magnetic fields and how many they are.
Yes,
there,
yes.
Right? Is that not dominating?
That's dominating in the sense that, so I haven't looked there too much into details, but they have like optimistic, a medium, and the pessimistic model. Good. So this is the medium model. The optimistic sits down here, the pessimistic here. To my understanding, in many cases, especially if you have like optimistic scenarios, from the population, if you have a large population of 100 million objects, you have always something very far in the tail. So that sometimes this can play a big role, and of course you probably are not very sure about what's happening in tails of distributions. But the signal here in the intermediate range and in the pessimistic range, which would jump up by like an order of magnitude, is coming from a large number of sources, so probably there these problems average out. In general, what's nice, kind of, is that the signal itself depends quadratically on this coupling. So to move this line really up here, you have to be like 3 to 4 orders of magnitude wrong with the signal calculation, which is hopefully not the case.
How does it scale with magnetic field? V squared?
Yes.
So
but in a complicated way, because this then affects the plus numbers and so on. So it's not strictly.
But magnet wars may be much better than ordinary pulsars.
Yes, that's true. But the signals here from the population, so we also calculated limits from the magnetar close to the galactic center, a parsec or so. This gives typically limits that are comparable, just this one single source. So yeah, so. But it's very close to the galactic center. With an FW profile, you have also a huge dark matter density. So certainly on that side one can also improve. But I have mostly thought about how to actually look at the data, so not so much the signal predictions up to now for the population. Good. So this are like this is the situation, and naively, if one just does like signal to noise calculations for SKA, one should get really deep into the coupling space and maybe hit the QCD line, but we will see in the future, because yeah, these searches are apparently severely limited by any systematics and any RFI that one sees in the spectrum, and it's a bit hard to predict for us what to expect in the future there. One kind of cool idea that my ex-PhD student Tom Edwards, who is now in Stockholm, put forward is, okay, so there are two kind of cool topics right now, axions and gravitational waves, so just put them together. And so what he proposed is a mechanism or a possibility actually for the far future, if Lisa is there, to get down to the QCD axion line. And the idea is, okay, let's hope that there's intermediate mass black hole, and which has like a very large dark matter density around it, and the neutron star spiraling in, then we could hope to see with Lisa actually the in-spiral, so we could detect the neutron stars going in, like at advance. Since there's a large axion dark matter density, the radio signal would be hugely enhanced, that we would expect. And from effects on the in-spiral signal, we could actually infer and make statements about the dark matter density around the intermediate mass black hole. So you would learn something about the mass around that black hole, dark matter density. You would ideally see a signal from like the single source, which would have funny like Doppler shift and whatnot. And in principle, this one source could then get down all the way to the axion line. But it's very far in the future, but it's fun to think about. So right, that's about axions. If you have more questions about axions, maybe it's a good idea to ask now. Otherwise, I will move on to deep learning. What time is it? Yeah, sure. Good. Good, so deep learning, that's here. It's kind of on the decreasing end of the hype cycle, at least gets close to the, how do you pronounce this, trough? Trough of disillusionment, but the prediction from Gartner is that in 2 to 5 years it will reach the plateau of productivity. So, that's nice. What did I want to do with this slide? So you see, deep learning is a cool thing, it will remain a cool thing, but the next cool thing is probably something else, and it's actually the next cool thing that I want to talk about is unfortunately not listed here, but it's called differentiable programming or probabilistic programming, mostly differentiable programming, and here an application for strong lensing image analysis. And this is in done in collaboration with a bunch of people from Amsterdam, Adam Kugan, Marco Chianese, which are both postdocs, and Cosio Karchev, which is a master student of mine who did actually quite a lot on this already. And yeah, Sidney Otten, who is also a PhD student and mostly involved in deep learning. Okay, so to give you an idea of what I'm talking about, it's useful to show Venn diagram. Sorry?
That would be nice.
Yes. So, in general, okay, imagine this is the set of all programming languages and algorithms, right? So then there is like a small subset that would be called deep learning. So these are deep neural networks. They work not both because we figured out how to do this algorithmically, but also because we have tons of training data. But deep learning really heavily relies on being able to optimize neural networks, so optimize models which have hundreds of thousands or millions of degrees of freedom. And the way this is done in practice nowadays, almost exclusively, is auto-differentiation. So the way a neural network is trained is you write down a loss function, which you want to minimize, and the language in which you write it down, PyTorch or TensorFlow or maybe something else, allows you to immediately calculate the gradients just by backpropagation, by basically applying the chain rule, with respect to everything that is inside that model. And then you can use this information to just optimize the model. So deep learning is very much, the success of deep learning is very much due to the fact that we have programming languages that allow automatic differentiation. And what's interesting is now that this ability of automatic differentiation libraries increased over time. So by now also you can autograd through solvers for ordinary differentiation, differential equations, or through, of course, for loops conditional statements. And so the amount of algorithms and programming problems that you can differentiate through increases over time and starts to increasingly overlap with physics simulators. And that's a very interesting fact, because suddenly you can actually think about solving high-dimensional problems on the side of modeling physical systems with the same tools that were previously used to make deep neural networks possible and successful. And that's kind of the same thing. So differentiability is at the core of the success of deep neural networks. And the latest neural network libraries really allow to not only do this automatic calculation, application of chain rule, but also integrate things like loops, conditional branching. And what's very peculiar about this is if you have like a model that is differentiable, you can suddenly plug together neural networks and physics simulators and other components, and they all kind of snap together like Lego. And you can build suddenly models that are more powerful than what you could just do with a physics engine or a neural network alone. And this has...
Well, you mean decent. You mean descent, not decent.
Oh, sorry, where do you have...
Third line.
Sorry.
That's it,
Yeah.
Descent with an S.
Thanks for pointing that out.
We all know it's decent.
Yeah, I know it's decent. So they are decent gradient descent networks. Yes, whatever. So, sorry for that. It's about running down the gradient. So I deleted